Okay, yeah, thanks. Thank you very much for the introduction. Okay, let's just get started. So first, a little bit about myself. So I'm an assistant professor at the School of Computing Science in Simon Fraser University. I'm the PI for the Multi-Agent Robotics Lab. And so some history, I did my bachelor's at UBC in Vancouver here. Later on, I did my PhD with Claire Tomlin at Berkeley, and then I did a postdoc at Stanford with Marco Pavoni. I really love multidisciplinary research. And hopefully this talk will be a reflection of that. When I say multi-prong, I guess here I'm only presenting two prongs. One is dimensionality reduction through system decomposition, and the other is optimizing software and looking at a low level into how the CPU and the computer memory works to try to improve computation speeds. Okay, so outline. So I'm going to just give a very brief introduction to the challenge, specifically focusing on the techniques I've been using, which is finite difference and a numerically convergent approach. And then I'm going to talk about the first, one of the ideas we've been trying recently to look at what we call chain systems, but more generally try to reduce the dimensionality of systems in a flexible way, depending on the different dependencies between the state variables. In the third part, I'll be talking about how to optimize software and some of the very initial things we have tried. So the third bullet point here is a very, very preliminary work, but I think we have some very promising results. And lastly, if there's time, I would like to highlight some of the novel applications of HJ PDE solutions in machine learning. So this is something that we've also been exploring very recently. Okay, so first, the challenge. My main application area with the Hamilton-Jacobi equation is in safety critical systems. So I think many of you are probably familiar with this. So here we need to formally verify the safety of systems by accounting for all of the possible behaviors. And we need to do this in usually complex environments involving unpredictable disturbances, such as wind or maybe even adversarial agents. These systems often have complex dynamics, and this is what leads to a lot of the high-dimensional challenges that we have. Right, and just to make things a little bit more concrete, I'm gonna, so here's one version of the Hamilton-Jacobi equation, which we often use. And to solve this equation, so actually we solved this equation backwards because we're interested in computing the backward reachable set. So this equation is solved on a grid, typically, and the idea is that by using finite difference, we get numerically convergent solutions, meaning that as the state space and time discretization go to zero, we should approach the exact solution. Of course, there are many ways one could solve the Hamilton-Jacobi equation, or even many versions of it. And I would say there's no right or wrong answer here. It really depends on your application, and different methods have different advantages and disadvantages. So I just want to focus a little bit on my motivation for using this numerically convergent method. So first, we get globally optimal solution. So that's always nice, very important for safety guarantees. We have a lot of flexibility with different variants of value and cost functions. So for example, suppose you define a value function like this, where you're interested in sort of a differential game between two players, and you keep track of some cost function, which is evaluated on a final state. So 0 is going to be the final time for this talk. So given this value function, you would then need to solve this Hamilton-Jacobi equation, right? So that's the same equation that I put up a slide ago. But I can give you some other variations. For example, here I've modified this cost function L to now include keeping track of L, the value of L over time, as well as making L time dependent. And if you define something like this, which is again very important for safety, as we do care about safety over some time horizon, then we can get some other version of the Hamilton-Jacobi equation, right? And then there are many other variants out there which we really care about. For example, we also care about reach-avoid problems, where you want to guarantee reaching of a goal while guaranteeing avoiding of some obstacles. So one nice thing about these numerically convergent methods is that we can relatively easily change the cost function to be something that is maybe not so standard, right? So something like the minimum over time, that could be difficult to deal with in general. Another advantage is we can analyze these disturbances for free in some sense, just because as long as we can solve this max-min, a point-wise max-min problem over here, we should be able to solve the Hamilton-Jacobi equation. And this is usually pretty easy if you have say control affine systems. Anyway, just a laundry list of things that we're kind of taking advantage of when we use these finite difference methods. So nonlinear dynamics. And the last one, we can represent sets of arbitrary shapes. And that's really because we have a grid-based representation. So here are two examples. The first one where we have a pairwise collision avoidance example between two cars. And here I'm showing a two-dimensional slice of the reachable set. This means that if you're inside the blue region, then collision is inevitable. So as you can see, this shape, even a 2D slice, is somewhat arbitrary. And in general, this is actually a three-dimensional set where the shapes could be very difficult to represent using some of the more common shapes such as ellipsoids or polytopes. And here's another example showing the reachable set for reaching a goal. Right, so these are definitely some of the advantages of using finite difference. I guess to go back to my previous slide, basically we're able to deal with the first three challenges, but where we're really having the most challenge is really the high dimensionality. So by offering all of these flexibility up here, we're kind of really paying for it in some sense with probably the least scalable method. So to give you some idea, with a lot of the existing toolboxes, we can solve four-dimensional problems. So and that will take hours. So these would be systems involving 4 state variables. And when we get to 5 states, we can now it will take days. And 6-dimensional problems tends to be intractable a lot of the times. So this is the big trade-off that we're making here. However, even with the limitations, I still want to show you some of the things we could do. So here we have some quadrotors which are flying pretty slowly, and we can see this automatic collision avoidance, it does work. So for some of these simpler systems, when we have drones flying near hover at pretty low speeds, even low-dimensional models are pretty good. On the other hand, we also tried some experiments on more sophisticated systems, such as an autonomous car here. So the car model, ideally, it really depends on what community you talk to. But from the NPC community, I think 7D seems to be kind of a small system for them. Or maybe the vehicle dynamics community. So 7D is pretty small. But for us, 7D is actually intractable. So we have to simplify the problem. It turns out that when we do simplify the problem, the cars, you do see the cars try to do collision avoidance. However, we have some errors that result in sort of positional errors up to 15 centimeters. And I would say this is maybe not acceptable for autonomous cars. And the underlying reason for that was that the rate of change in turn rate, so the way, like how fast you turn the steering wheel, as well as how fast acceleration is changing, that was actually important. And we were not able to model that because we had to simplify the model. Okay, so that was basically an overview of the challenges. So next I want to talk about one of the techniques we used for dimensionality reduction. So here, so this is work with my master student, Anjen Lee. To motivate this work, I would like to start with a very simple example here, the 4D quadruple integrator. So basically, just integrate a chain here. So the way we kind of abstract this dynamics is by using a state dependency graph. So what we have here is that Z1 dot depends on Z2. So we draw an arrow between Z1 and Z2, and these nodes of the graph are basically the state variables that we have. So whenever the time derivative of a state variable depends on some other variables, we would draw an edge between the former to the latter. So for this system, we have just a pretty simple chain here. Okay, so So when it comes to, so now that we have this graph, we can think about breaking this graph apart into smaller subgraphs. And the first option is actually, well, why don't we consider 3 two-dimensional systems? So this means that we simply have Z1 and Z2 grouped together in a subsystem. You kind of realize now that, well, in this subsystem, there's a variable that is missing, right? So Z3 is not part of the subsystem states. So the way we represent that using the graph would be, well, Z1 still has a directed edge to Z2, but then we have a sort of a dashed edge here to Z3 to represent that Z3 is important for the evolution of the system, but it's actually missing from the system. So this decomposition would be depicted overall by these 3 subgraphs, and 2 of these have missing variables. So this is simply a process of how you would decompose. I will get to what you do computationally with these subsystems in a bit. So this is actually one option. Another option is, well, we can also consider 2 3D subsystems. So here we would have something like perhaps Z1 to Z3 and then Z2 to Z4. And then we would have the resulting graphs where in the Z1, Z2, Z3 system, we will have Z4 as the missing variable. Okay, so hopefully the way we sort of consider subgraphs makes sense. It's not too complicated. And by having multiple options, in general, if you consider a much larger system, you can kind of imagine there could be many different ways of breaking this original graph into different subgraphs. And this is a natural way in our method for trading off efficiency versus accuracy. The larger your system is, we realize that we'll have fewer and fewer of these missing variables, and therefore some of the options will be definitely more accurate, whereas some of the other options will be trading off accuracy for efficiency. Okay, so let's go back to this 3 2D subsystems example. So let's start off with the last one here because it's the simplest. We can kind of see that Z3 and Z4, they're self-contained, meaning that there are no other variables that they depend on. So we can simply just do this 2-dimensional computation and maybe we'll get some, in our case, some reachable set. And so not only do we get some reachable set, we can actually interpret this reachable set in the following way. So given any Z3 value, we will induce some bound of Z4. And this is going to be very important when we consider the next subsystem, which only has Z2 and Z3, but it also depends on Z4, which is actually not present in the system. So here, in order to still model the effect of Z4, which is an unknown variable, we use the worst case Z4 given all the available information that we have. In this case, this information is in the form of, for every Z3, we know the bounds on Z4, and we would pick the worst Z4 within these bounds. So this idea is actually not new. I believe one of the earlier works that had the idea of projections and considering worst case about certain variables, I think that was presented all the way maybe in, I want to say 2003 by Ian Mitchell. But here, I guess the main difference here is that we're kind of looking at, we're using more information here, which is dependent on one of the state variables that we have. In addition, as you will see, we're going to be doing this in a multi-stage manner. Okay, so now, now in this Z2, Z3 subspace, we have the worst case Z4 for every Z3. So then we can kind of do this reachable set computation by treating Z4 as a disturbance. So then maybe we'll get some reachable set in Z2, Z3 subspace, something like this. So now we can apply the same argument again. This reachable set in this subspace will induce a bound for Z3 given a value of Z2, right? So for every value of Z2, you can see a different bound for Z3. And this again will be very important for the evolution in Z1, Z2 subspace, where we can now treat the missing variable Z3 as a disturbance bounded by these bounds, and these bounds actually depend on Z2. So then eventually we'll get some reachable set in all of these subspaces. Of course, we're going to incur some degree of approximation here, but we're trying to minimize the degree of conservatism because we're really trying to use all the information we have every step of the computation. So the result is actually an over-approximation when it comes to reachable sets that guarantee safety. And the way we can reconstruct the full dimensional reachable set would be to first back project all of these sets in two-dimensional space up to 4 dimensions, and then we can take their intersection. And here, because we have over-approximations, we can still guarantee safety. Okay, so let's look at the computational complexity of this process. And then we're going to first look at the memory requirements. So I think the memory is pretty straightforward. We basically have 3 two-dimensional sets. So we basically need a few two-dimensional arrays to store our solution. So here, the memory requirements is basically the maximum dimension of the subsystems. And pictorially, this is given by the number of black nodes in the subgraphs. Time. So time is actually a little different. So obviously, we need to compute these value functions over a 2D array in this case. But in addition to that, we also have to search over these missing variables. So for example, when we do the Z1, Z2 computation, for every Z2, we have to determine what is the worst case Z3. So this adds another dimension. Of course, searching over Z3 is actually is going to be much faster than doing finite difference. So the third dimension here is actually much faster than the computation of the value functions here. But again, we have to be honest. This is actually, in general, a 3-dimensional problem, a 3-dimensional computational problem. So for the time complexity, we have the maximum number of nodes, including these blue nodes here. So 3 in this case. Okay, so for the second option, I'll just go through it very quickly. Again, we can start from the end here, Z2, Z3, Z4, and we see that it's self-contained. So that's fine. We can do that computation exactly. And by doing the computation here exactly, we will have a 3-dimensional set. And this three-dimensional set would induce some bound on Z4 given every combination of Z2 and Z3. And this information would be used in the second computation for this subsystem Z1, Z2, Z3. And here we can then treat Z4 as a disturbance with these bounds given by the first computation. So exactly the same thing, except now you can already kind of feel the improvement in conservatism just because we have a much better bound on Z4 because we're given both variables here. Okay, so some results. So for the quadruple integrator, we try to do this using 3 2D subsystems. The blue is a ground-truth reachable set, and the green set is the approximation. So we can see that we have an over-approximation. So I guess here the exact shapes are not so important. The main point is really that we have a larger set and over-approximation, which means that we're guaranteed to maintain safety here. And the computation time gains are really large here because we're going from 4 to 2D. So from 420 seconds to 2.5 seconds. We also used a 6D bicycle model. So this is a common model used to model autonomous vehicles. Okay, so now the dynamics look a little more complex, but we can abstract these dynamics as a state dependency graph here. So something like this. And so now how do you decompose this into smaller subgraphs? Well, for now, there's actually no automated way. We have to kind of look at this and do it by hand. So this is what we came up with. So let me just go through maybe just a couple of these. So the first one, X, Vx, Vy. So this is X, Vx, Vy. So everything up here. And then we can kind of see that X also depends on psi here. So that's why we have this missing psi variable. Same story with the y, vx, vy. So we have this subsystem here, which is missing the psi variable. So that's what we have here. We also have a couple of self-contained systems, and basically now there are many more subsystems, but the procedure is still the same. We start off with these self-contained systems for which we can compute exact reachable sets in these subspaces, and then we work our way back to sort of use the information from these computations to define bounds for our missing variables for these other subsystems. Okay, so in this case, we have 3D value functions that we have to store, right? Because the largest subgraphs with the black nodes are 3 nodes, so 3D value functions to store. And we have 4D computations because the largest graphs also include 4 nodes if you count the blue nodes as well. Again, the searching over these missing states, that's going to be a much faster computation than the computation that is done on the black nodes. For this problem, we consider this, I would say, pseudo-practical example where we have a parking lot. So these are the parking lots where you have the cars parked diagonally. So in the red area, we must move towards the right. And we must sort of face, so the speed must be forward and the orientation also must be forward. So we defined our unsafe set to be the complement of this. Again, I guess it's not, again, we have some numerical results here for the 6D problems. So the red is the target set, and we simulated 2 trajectories. One, the star, which begins outside of the reachable set, and the cross here, which begins inside the reachable set. And when we ran the simulations, we saw that the blue trajectory was able to remain outside of the reachable set and therefore outside of the target set, which means it's safe. Whereas whereas the black cross, it started inside the reachable set, and eventually you can see down here that it did collide with the target set. So the angle dimension here is periodic, so that's why you see the black trajectory going up here, and then it shows up down here. So those were 2 examples, and so right now we also looked at some other systems. For example, a 5D car with thick dependency graph as follows, like this, and then we can sort of say, well, suppose that your computational capabilities are a maximum of 4 dimensions, then this is how you would decompose the system, and you would go down from 5-dimensional computation down to 4-dimensional, like big O of k to the 4 time and big O of k to the 3 space. And then we can also look at something else like a 6D planar quadrotor. Again, the same story, right? This is from the dynamics, we first obtain the dependency graph, and then we can now use our creativity to construct these subgraphs. And in this case, again, we limited ourselves to maximum 4-dimensional problems. So now I want to discuss future work and limitations. Of course, these go hand in hand. Any limitation would be future work. So the first one is leaking corners. So here, when we reconstruct the full dimensional reachable sets, we either take the intersection or union of these reachable sets. So this is actually a pretty common, it's a common operation whenever we work with projections. So then the leaking corner problems would kind of come into play here. So what this means is that if we want to avoid some target set, we must take the intersection and not the union. And if we want to reach a target set, then we can only take a union. So this is, again, is a limitation that we ran into for many of our previous projects. Again, I think Claire Tomlin's group is working on this right now. Maybe we can catch up with them on their progress. The second limitation is more specific to the way we decompose into subsystems. So let's just go back to our example where if we wanted to compute a set in the Z1, Z2 space, we would need some kind of bound on Z3, the missing variable, which is obtained from the set in the Z2, Z3 space. So one of the problems we're seeing is that suppose you try to access some Z2 for which there's no reachable set. So there's no range of Z3. So what do you do in this case? So this is something that we're looking into. It seems almost like a trivial problem. Somehow if there's no set in Z3, it should help us. But in this case, we haven't figured out what to do with that. So it seems like it's a paradox somehow. Another interesting thing that we would like to look into is that as we try to decompose more and more complex systems, it's going to get more and more tedious to handcraft all of these subgraphs. So we're also working on an automated way to kind of search through the graph to find a reasonable decomposition automatically. So that would definitely help a lot. Okay, so that was dimensionality reduction. So here I want to switch gears completely and talk about software optimization. So whereas dimensionality reduction is basically saying, well, the problem is too big, so let's reduce the problem into something tractable for us to solve. And this, for optimizing software, we're saying, well, let's make it tractable to solve larger problems, right? So these are basically complementary approaches to help us eventually hopefully solve larger and larger problems. One of the motivations for starting this work is that a lot of the progress in deep learning, very, very popular field these days, depends on being able to utilize a large amount of compute resources. And from my personal experience, I find that a lot of the PDE solvers, they're often run locally and they're not really maximizing the use of compute resources. So this is a direction that we want to go into. So with my collaborator SFU, Arvind Shiraman here, and our student Min Bui, we're asking the question of, can we alleviate computational challenges via software optimization? And the goal, again, is to consider different hardware such as CPUs, GPUs, perhaps even FPGAs, which would be very useful to deploy on real robots, as well as, of course, cloud compute. And this hopefully will allow us to analyze higher dimensional subsystems. So that's definitely one application. But another application we're looking into is perhaps even for some of the smaller 3 to 4 dimensional systems, we can even do these computations in real time. And this would definitely solve a lot of the issues of requiring a known environment for these reachability computations. Okay, so just a very quick overview of what goes on in solving the Hamilton-Jacobi equation. So this is the equation, and let's just call this the Hamiltonian as we're familiar with this. So basically what happens is you start with some v function. After you have some so given the v function, you have to compute this gradient, which could have multiple components here. And then you would have to use the gradients to compute your optimal control and disturbances. Afterwards, you plug into your dynamics, your f or dx dt, and finally you get your Hamiltonian here. And after you get your Hamiltonian, you would then do an integration time step by discretizing this partial v, partial t term here. So that's basically at a high level what we're doing when we use finite difference. So in terms of optimizing these operations, so we're going to consider a few different things. So these are the things that we're going to talk about. So let's start with memory, locality, and loop order. So some background first, actually. So this is a computer memory pyramid where at the bottom is something probably many of us are familiar with. So these are stuff like your hard drives, your, I guess nowadays SSDs, where they're, I guess, comparably very, very slow in terms of communicating data back and forth inside a computer. However, these typically have very, very large capacity. As we move up the pyramid, we get to the main memory. So now we have much, much faster communication times, so much, much less access latency, but also much, much less capacity as well. So the main memory is something that we're probably familiar with as well. And then we have the cache memory, which is part of the CPU itself, even faster, even smaller. And then we have at the top level, the register memory. What we're focusing on now is looking at the cache memory. So what happens with the cache memory is that a lot of times you would copy information in the main memory into the cache. And if we can use the cache as much as possible and minimizing copying between the main memory and the cache, we, in theory, should be able to speed up the computation a lot. So here's one illustration of this. So first, memory is linear. So when we solve something on a grid, this is a very useful picture to help us understand what's happening. But inside a computer memory, we really have these grid points in a line, something like this. Whenever we try to access some memory location, so let's say we want to access location 0, 0 on the grid, the neighbors of this memory location will be loaded into the CPU cache to improve access times. So for example, when we access 0, 0, perhaps all of this memory will be starting from 0, 0, going up linearly, will be copied into the CPU cache. And in terms of the grid, it might look something like this, where perhaps we cover the entire first row and maybe a bit of the second row, something like this. So now if you just look at this from a very, very basic level, you kind of realize that when you solve the PDE, typically it's going to be through some kind of for loop, nested for loops or nested loops in general. It's going to be much faster if you loop over horizontally first, because then you'll be accessing data in a cache, which is much faster than accessing data in the memory. So if we just go first row, second row, that's going to give us the best computation times. In contrast, if you start to go downwards first, well, 0, 0 will be fast, that's in cache. 1, 0 is also going to be very fast, that's in cache. But as soon as you get to this node where you're now accessing data that is not in the cache, the computer would then have to copy stuff from memory into cache. So you're kind of not really maximizing the use of all the information in the cache. So this is why, this is what I mean by memory, locality, and loop order. So hopefully by kind of writing our loops in the right order, we can speed up the computation. And a very straightforward extension of this would be parallelism. So here, instead of copying the first chunk of memory into cache, we can actually have two starting points, and then we can copy sort of the green and the blue parts simultaneously into cache. And this will allow the CPU to do computation on both parts of the grid at the same time. So these are, I guess, pretty straightforward optimizations, I would say. So again, this work is, so the work we're doing in this area is actually very, very preliminary. We have some very promising results, and we're still trying to understand deeply what the results mean and what are some other ways of improving computation times. The way we're implementing these optimizations is through the framework called HeteroCL. So here's a link to them. But just to give a very simple overview, what HeteroCL allows us to do is we can start with a naive version of the code. Let's say that we just simply use a simple nested loop, right? So this is something that we all know how to do. When we talk about parallelism or maybe loop order, any kind of these optimizations that we want to do, it really involves rewriting your loop into, for example, multiple for loops that you may execute at the same time, for example. And perhaps you don't even iterate. So if I go back to the grid, sometimes you may not even want to iterate through the entire row before going to the next row, right? So there are many things we may want to do to optimize the computation. So what HeteroCL allows us to do is it allows us to start with a naive version of the code and then transforms this code based on how we want to optimize it. And there's no need to re-implement anything here. So we don't need to manually rewrite our for loops in a different way. We simply use these functionalities built into HeteroCL. And one really nice thing is if you imagine manually implementing these for loops, you can kind of see that it's very easy to make a mistake. But under the HeteroCL framework, we can guarantee that the algorithms will not change. So anything you do with a simple nested loop, so the correctness of that algorithm will not change. So that's really, 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 really nice and convenient. So the main algorithm is actually written in Python. So this is pretty user-friendly. And what HeteroCL does is it will translate the Python code into high-performance C code. So this really makes this a really useful tool for reusing and optimizing code for different hardware platforms. So for example, CPUs tend to have fewer number of parallel threads, whereas GPUs have many more threads, which are less powerful. And when it comes to FPGAs, now you can completely customize your memory and your cache, right? So these are so if we want to optimize software for many different hardware, we should definitely not try to do any manual implementation. So again, very preliminary results. So we tried this framework on the Dubins Car, and the only thing we have done is simply have the nested loops run in the right order, as well as adding some parallelism. So here, when it comes to the computation times, I'm reporting these as the number of seconds per integration time step. So using the MATLAB toolbox, so if we do this in MATLAB, we have something like anywhere from 0.05 to 0.1 second, of course, depending on the grid size. And by doing these very, very obvious, I would say probably pretty obvious optimizations, we actually get a speed up of anywhere from 26 to 38 times just on the CPU. So this is on a desktop computer. We find that the speedups kind of depend on what processors you used. So for example, we also tried this on a pretty old laptop CPU. And in this case, we actually found a speedup of something like 55 times compared to MATLAB. So this is, I would say this is just the beginning. We only have the right loop order, which is, it's pretty obvious, and we try to parallelize the computation a little bit. And there's definitely a lot more room to speed up here. We tried another, so our first application to kind of a more practical problem would be a 6-dimensional underwater vehicle with these dynamics. So I'm not showing the full dynamics here. They're quite long. So here the practical problem is there are a lot of very strong disturbances underwater, and we're trying to use the Hamilton-Jacobi equation to derive sort of a guaranteed tracking error bounds on for trajectory tracking. And this involved computing a 6-dimensional system. Here we use the grid size of 25 to the power of 6, so 25 grids in every dimension. And it took 5.1 seconds per integration time step. And this 6-dimensional system used to be intractable, so we're really happy to see that we're actually able to do this computation. So I guess here are some results for the tracking error bounds. Again, maybe not so meaningful here. The point is hopefully convince you that we do have some results and that this is actually a tractable computation. In terms of the total computation time, it really depends on how many integration time steps you're doing, and that kind of leads us to another thing that we have not considered, which is that depending on the parameters of our problem, the ODEs could be very, very stiff. And when you have a very stiff ODE, you may have to run many, many time steps. So we found that with this system, if we choose the parameters such that they're not stiff, then we can do a computation over a 20-second time horizon in about 1.5 hours. So that's actually quite, I would say, honestly, it was very surprising to me when I first found the results. So 1.5 hours for a 6-dimensional non-stiff system. When we used some parameters that made this system pretty stiff, it turned out that we needed 10 times more time steps. So it turned out to be about 15 hours to solve the PDE for to solve the 6-dimensional PDE for a stiff system. We also did a 6-dimensional humanoid model. So here we simply computed the backward reachable set, and here it was 2 seconds per time step. Again, I guess the point here is that previously with these 60 systems, we have to be pretty clever with decomposition, perhaps, or maybe we needed to use many of the other methods that involve, for example, other forms of approximations like ellipsoidal or maybe polytopic approximations. But here we're simply just brute forcing this. Again, some results which are maybe not so meaningful now, but at least we can do it. So like I said, this whole line of work is just a starting point, and we think that we can definitely do a lot better by optimizing the software even further. So some of the things that we're thinking about are tiling and dynamics dependent loop order. I'll just give a very quick overview of what this means. So let's consider tiling first. So tiling involves loading a part of the memory into the CPU cache. So let's say that we initially load this blue region of the grid. And when we do tiling, we want to compute all the derivatives in every dimension using this data that we have, so that we finish using the data before we load in any other data, right? So that after we finish with the blue data, we can now use the green data. Again, it's not a very sophisticated concept here. And so the idea here is to minimize data movement, right? And the key here is to use hetero CLs to help us implement something like this without any tedious coding, so without any manual implementation of complicated loops. So that's tiling. And next, dynamics dependent loop order. So again, I'm going to go back to the Dubins Car example, where we realize that the theta dynamics do not depend on x and y. So from this perspective, it seems like if we were to write a nested loop involving these three variables, it would actually make sense to iterate over different theta values in the outermost loop, so that when you iterate, so that in the inner loops, the theta values would mostly be constant, and you don't have to keep changing the theta values. So remember how I said a while ago that the loop order is important, but here I would like to customize the loop order, right? So in order to customize the loop order, we have to combine this idea with tiling, where we kind of manually specify what part of the grid we're doing combination over. And once we specify this, we should be able to customize the loop order in whatever way that benefits us the most, given the system dynamics. So besides these software optimizations, we also would like to look at many potential applications. And I really think that we open the door to many applications. So one of these I mentioned, real-time reachability computations. So imagine you have a 4-dimensional system where previously it would have taken, say, minutes to an hour to compute. But now let's say that we're able to compute this in 0.1 second, so at 10 hertz. So this will really open the door to throwing a robot down into an unknown environment and have the robot sort of do these reachable set computations in real time as the robot senses the environment. So obviously, in general, a purely brute force method may not be the best. But of course, our better computational capabilities will definitely complement any of the other, say, dimensionality reduction techniques really well. Another thing we want to study is actually model fidelity. So this comes back to the car experiment that we did. So it will be kind of interesting to have many different models of the car, let's say 3-dimensional up to perhaps 7 or 8-dimensional models. And then we can do some reachability computations, and we can see, at what point is the model fidelity good enough for us to actually implement collision avoidance on a car. And of course, we can't forget that we would like to release an easy-to-use toolbox where everyone should be able to specify their problem let's say in Python, and all of these optimizations under the hood would be hidden from the user. So that would be that is sort of what we're aiming for, hopefully by the end of this year. Okay, so that was so I think I have maybe 5 minutes to quickly go over just to highlight some of the novel applications of HJ PDEs in machine learning.
Yes, go through.
Sorry?
Yes, of course. You have even a little bit more.
Okay, thank you. So here, I want to focus on reinforcement learning and visual navigation. So this is related to computer vision here. So let's begin with reinforcement learning. So here we're looking at model-free reinforcement learning. And just to give a very quick overview, Here, suppose we're given a simulator of a system or perhaps a real system and some reward function. A reward function is basically, think of it as negative cost. So nothing too special except for terminology here. So we would like to determine some locally optimal policy, control policy, without knowing the model of the system. So no dynamics here. And the way we do this is simply by trial and error. We try these control policies, and these would typically involve some kind of exploration and exploitation. And then we use these control policies. So given how much reward we collect in our experiments, we would then adjust our policies to hopefully receive more and more reward in future iterations. Again, it's just a very high-level overview. And some of the advantages of model-free RL is that it doesn't require system dynamics. That means it actually allows us to find mappings from sensor data from sensors directly to the control. So sometimes that can be useful. And the other thing is that RL can be scalable to larger systems when we use function approximators. Disadvantages, of course, there are many disadvantages, but I think the two main ones are going to be poor sample efficiency. So you may need to run simulations many times before you can learn something reasonable. And it can also be very difficult to incorporate knowledge of system behavior. And the last bullet point here is actually where Hamilton-Jacobi PDEs come in. So a lot of times in RL, when we define the reward or the cost, negative cost, we typically define something like, if you reach the goal, you get a high reward. If you collide with an obstacle, you get a very negative reward. Otherwise, you get zero reward. So this is actually pretty bad for learning, because most of the time your system will not really get any reward, or maybe after many time steps, you get a very negative reward, and you're not really sure why you got the negative reward. Right? So this is one of the issues with having a sparse reward like this. And some of the ways people have been trying to get around this sparse reward is by using heuristics for reward shaping. So instead of using a reward like this, people can try using perhaps distance to goal. Right? Maybe you get more reward if you're closer to the goal. So this seems kind of reasonable, but as control theorists, we kind of know that while distance is not the whole story, right? We need to consider all the states. For example, heading is important, speed is important. So distance to goal, although it's a very easy reward, maybe is not the best. Another thing that people have tried is inverse reinforcement learning. So this is basically first, through expert demonstrations, learn the reward function of the expert. And then through this, and then when we actually try to train an autonomous agent to do the same task, we would then use this learned reward. But unfortunately, this requires expert demonstration. So that's the downside. So with my PhD student, Shibo Liu, we have been using the time to reach function as a reward function. So the time to reach function is just the minimum time required to reach the goal from any state. And this is basically, you can compute the time to reach function by solving the Hamilton-Jacobi equation. So normally this would be it would be intractable for complex systems. Also, you would need a model for this. And the way we get around this is by computing the TTR function using a simplified system model. And this will help us approximately account for system dynamics. So we can kind of think of this as, suppose you have a full-scale autonomous car, and we're actually not able to compute time to reach for that full model. But let's approximate that model using something like a Dubins Car, right? It's not the best model, but it approximately captures the system dynamics. And then after we compute this time to reach function, we can then use this function as the reward in the higher dimensional system. So the intuition here is that the car, we want to give a high reward for a car being over here because it can directly move forward to the goal. And for this other position, because the car is facing the wrong way, we should actually give it a low reward because it has to turn around, right? So this can be quantified using the time to reach function. So here we have the original problem in a very high dimensional space, and we compute a time to reach function in a small subspace that is tractable for us. And I mean, this is a very, very simple idea, but surprisingly, this works pretty well. So we tried this on a 6-dimensional problem of a quadrotor trying to fly from this starting position to the goal region up here while avoiding obstacles. And so here, this graph is showing basically a summary of the results. On the y-axis, we have the success percentage when we try to execute the control policy. And on the x-axis, we have the number of the amount of learning, the number of iterations of learning. So here we're using a value-based RL, DDPG, for those of you interested. So this blue line is basically using TTR reward shaping. And we can kind of see that it's able to learn basically pretty close to 100% success. For the other lines, we're trying many different kinds of reward shaping, including sparse reward, as we discussed, and a few different distance rewards with different hyperparameters to weigh different dimensions in the state space differently. So none of these actually worked in this learning method. We also tried other learning techniques, other reinforcement learning techniques. So these are actor-critic methods. So I think in this case, we tried PPO. So in this case, we can see that our TTR reward is able to perform pretty well after some learning. For the distance-based rewards, if we tune the weights between the different dimensions of the state space, we are actually sometimes able to achieve pretty good performance. But again, that kind of requires some tuning. Whereas in the TTR reward, we basically compute the TTR and that's the end of it. There's much less hyperparameter tuning. So that was reinforcement learning. And now I want to talk a little bit about visual navigation and computer vision. So this is in collaboration with my student, Anjian Lee again, and Claire Tomlin's lab. So we have Samuel here and we have Varun over here. So here the goal is to navigate through an environment using cameras only. And the motivation here is that cameras are pretty cheap, right? So they're kind of ubiquitous. So we can presumably deploy robots at a very large scale. One of the purely deep learning methods would be to try to learn how to map directly from pixels to actions. And I would say that for the most part, it is not so efficient. So here we're taking a control-inspired approach where we map pixels to waypoints. So let's say you have a robot that wants to reach some goal over here. Instead of outputting the actions, we want to output a waypoint and then using control theory to plan a trajectory to the waypoint. And the motivation here is that there's no need to learn what we already know, right? We already know how to get to a waypoint, a nearby waypoint. So why do we need to learn that? So this idea was originally proposed by Samuel, Claire, and also Jitendra Malik in Coral 2019. And the idea is that we want to train in simulation. So basically, we kind of in simulation, we would render many different images. And then for every image, we would kind of say, well, given this image, this should be our waypoint. And given many of these image waypoint pairs, we should be able to train a neural network that will choose the right waypoint. And it turns out that this method is actually very transferable to real life. And I think some of the robustness is coming from the fact that we're combining control and learning. So I think the main question we're asking here is, how do you generate training data? Given an image, how do you know what a good waypoint is? Right. So one of the simple ways of determining a waypoint would be perhaps we can use simple heuristics involving distance to goal and distance to obstacles. And if you try that, you will kind of find that the training data would look something like this. In large open spaces, we are able to obtain training data that says you should go here and then here and so on. But once we get into a narrow space, we'll find that we're not actually able to generate any training data that goes through the narrow space. And the reason for this is really that if we try to force points in this narrow space, we'll find that when we train a neural network, the neural network will have some errors during test time, and the errors will basically cause the robot to collide with the obstacles. So in order to try to make things a little robust, if you use some distance-based training data, you should actually have some safety margin. However, with the safety margin, we now lost the ability to go through doorways. So naturally, we're going to do supervision by Hamilton-Jacobi solution, right? So again, distance is not the best heuristic, because if you go through a narrow doorway, even though you're very close to the obstacles, as long as you're facing the correct direction, you should be okay, right? You can be very close to the obstacle as long as you're not also facing the obstacle and moving toward it. So let's say that you see an image like this, right? We can now compute something like the time to reach and time to collision functions. Again, these can be done by solving the Hamilton-Jacobi equation. And then we'll have some kind of map of the time to reach and time to collision, something like this. And using these functions, we can then decide, okay, what is a good waypoint? A good waypoint would be something with a small time to reach and a large time to collision. And by basically implementing the new cost function, we're actually able to smoothly generate training data that will go through narrow pathways. And this is where I think a lot of the work that we've been doing on addressing computational challenges is very important, because to train a neural network, we require a lot of data, and which means a lot of different, we need to solve the Hamilton-Jacobi PDE many, many times. So I think right now for our project, I think we spend maybe almost 24 hours generating data. If we can speed that up by a factor of, say, 100, then, I mean, obviously training will be much, much faster. So now, in terms of the training data quality, we start with the distance heuristic here, which is not so good. With the Hamilton-Jacobi PDE approach, we can kind of pretty easily, during training, we can easily see that, okay, as long as we face up, we don't have to worry about being close to the obstacles. And then we can kind of see this in a few different scenarios here. And so we actually solved the HJ PDE many times to generate training data, and then we use the training data. So all of this was done in simulation. Using the training data, we trained a neural network that predicts waypoints, and we're able to directly deploy this neural network on a real robot without any additional training or tuning. And we actually, we demonstrate much better success rate compared to previous results. And what's really interesting here is that through this Hamilton-Jacobi training data generation method, we see that in these bar graphs here, the blue is success rate of our method and orange is success rate of the baseline. So we can see that we have divided the tasks into hard, medium, and easy tasks. And the difficulty of task depends on the narrowest space that the robot must go through to reach the goal. So for the hard tasks, meaning that there's only a 0.2 meters clearance around the robot. So these hard tasks is where we're gaining a lot of performance. So this basically shows that Hamilton-Jacobi PDEs being used as training data is very effective. Okay, so I think I'm right on time. So thank you very much for listening to my talk. If you have any questions, maybe we'll have some time for questions, but if not, please email me. I'll be very happy to answer your questions by email, or we can even schedule online meetings to have any kind of discussion.
Very nice. Thank you very much for the talk, Mo. I guess we have time for one short question. If anyone in the audience want to make a comment or a very short question, please raise the hand. Oh, Gary. I think I unmute you.
Am I unmuted?
Yes, I hear you now.
Oh, yeah. Hi, Mo. Great talk.
Thank you.
And yeah, I would say based on our approach, which wasn't quite this, but what you're doing with, combining these is, I think, the way to solve some of these problems, no doubt. To use, it's a great idea. I think there's a lot to do with this kind of approach.
Yeah, definitely think so. I'm glad you agree.
So that's my comment.
Okay, thank you. Yeah, lots of work to do.
So fantastic. So since we have like a 1 hour lunch break, so what I would suggest, like it's anyone that have a question, want to make a comment, to reach directly Mo. And I thank you very much again for this very nice talk.
Yeah, thank you. Thank you for organizing, and thanks everyone for joining.